Okay, we've begun recording. So just to give the recording some context, there was a question about cellular respiration, specifically relating to the citric acid cycle, which is pictured here. And just the steps of it. So to contextualize that, I am going to first talk about what this is even for, because that's kind of the main idea of the citric acid cycle. Why do you need it to turn around twice per pyruvate? Why do you go through the seemingly extra steps of taking a 2-carbon molecule, which you see up here at acetyl-CoA, there's carbon, and then coenzyme A, and then sticking the 2 carbons you get from that onto oxaloacetate to form citrate? Like, what is the point of all this? Why would we even do it? It seems like a lot of extra work. So the point is important, and I'm gonna do that guy first. So in order to do this, we need to draw some things. Every time I take it apart, it wants to ask me about switching to tablet mode. No, go away. All right. So we're going to take our brains on a journey away from all things citric acid cycle for a moment, and just think about something that's relatively easy to understand and that has a big impact on our lives, and that is dams. The kind of dams that we use to generate electricity specifically. So here I have a landscape. I've drawn a wall. That's my dam. On the left side, I have water. And on the right side, I have water as well, but a lot left, or a lot less rather. And then let me go ahead and all right, so that's pretty easy to understand. And, you don't even really need to know anything about science to understand, like, if I put a bunch of water up, it's going to want to go down, right? Mm-hmm. So if I were to rip this wall out, the water would go this way until the 2 sides were equal. But I can't because I put a wall in the way. So the water wanting to go down but can't represents potential energy. And now we're getting a little bit into thermodynamics, but I promise there'll be a payoff. So by putting water up, in this case, we just built a wall in front of it, and then we're like, haha, you can't flow down the mountain. Unless I say you can. Water wants to go down but can't, so that equals potential energy. Another way to say potential is stored. Energy that you could use, but you're not using right now. So if we want to generate electricity using this structure, how do we do it? Well, we create this situation where water really wants to go down because we've put it up, but it can't, which means we've stored a tremendous amount of potential energy. If we then control the way the water goes down, and I'm about to draw a terrible turbine, so just bear with me. It's not going to be good. I'm sorry. So a turbine has a rotor and then it has a bunch of fins that kind of look like this. And they're shaped that way because you want the water to cause the thing to turn around. So it's basically like a fancy sideways water wheel. And let me label that since it looks nothing like what I intended it to. All right, so now that I've drawn my god-awful turbine, I'm gonna be like, all right, water, you wanna go down? Sure, go down. And I let my water go down, which is nice of me. Oops, I want discolor. There we go. So now I'm letting the water go down, but I'm like, well, you can only go down the way I want you to go down, which means it has to flow past the turbine and then it goes out where it wants to be. Hooray, yay, the water is now at its preferred location. That's great for the water. The water's work is done. But what happens to the turbine as the water flows past it? It spins around. So here I was talking about potential energy. Energy that you could be using, but you're not. When I let the water go down, but I have it go past the turbine is spinning, and that represents kinetic energy. So I've now turned stored energy into energy that I'm using. Awesome. So for me, what that means is the part you don't see in this drawing is that surrounding a turbine is an electromagnet. And for reasons that I won't even try to explain because I'm not an electrophysicist, if you put an electromagnet around a turbine and you let the turbine spin around in it, it makes electricity. So the kinetic energy is important here because the kinetic energy is converted into electricity. And that's why I'm currently able to talk to you, use my laptop, and although it is dark outside, I can see in my home. Awesome. So what does that have to do with the citric acid cycle? Well, electrons are where I was trying to get. So, really quick tutorial. I'm going to draw a really big, really sloppy mitochondrion. Whoop. So here's the situation. There's a big membrane on the outside, and then there's a smaller membrane that's scrunched up on the inside. So that creates two compartments in the mitochondrion. There is the intermembrane space, and then the inside, which we call the mitochondrial matrix. So here's how your mitochondrion is like a tiny dam. There are, and I can't finish drawing them because that's not a good use of our time. There are so many more protons in the intermembrane space than there are in here. So it's just like the dam. I've put a bunch of protons in a space and they really, really want to go in here, but I'm not going to let them. I'm going to make them go through something if they want to go in. So it's just like a dam where the water is up, it really wants to be down. And I'm like, all right, you can go down, but you have to go past my fancy doohickey if you want to go down. And that's how I get electricity. Same deal here. So proton is allowed to go down, but it has to go through a protein called the ATP synthase. And just like a turbine, ATP synthase actually turns around. So the protons are the water. They flow down their concentration gradient, through the ATP synthase, which turns around, converting potential energy into kinetic energy. And that kinetic energy is used to make ATP, which is, of course, the goal of all this, right? So now we get to think about why we need the citric acid cycle. So a word that you see when you start to look at glycolysis and the citric acid cycle and the electron transport chain is this word or set of words, reduced electron carrier. And if you've done your due diligence as a student of doing the memorizing portion of learning, when you see these words, what should pop into your head is either this, oops, 2, or this. So these are reduced. In redox reactions, reducing means putting an electron on something. So if I were to reduce my dog Blinko, who is sitting next to me, I would take an electron and I would stick it on him. And then oxidizing is the opposite. It's taking an electron away. So if I were to then oxidize Blinko, I would just take the electron back off. So these are reduced because an electron has been added to them. So we want our electron carriers to be in the state reduced. We want that because the electrons they are reduced with, they have to carry, and you want them to carry electrons to the electron transport chain. I'll show you why that is in a little bit. I still want to talk about the citric acid cycle, but the short version is so remember when I drew that mitochondrion just now and I put a bunch of protons in between the outer membrane and the inner membrane, creating this gradient where protons want to flow down. But you know, I had to make that happen somehow. So the answer to how did that situation come to be that those protons got there, creating that potential energy, is electrons were used to do that. But the electrons have to come from somewhere. Electrons aren't just free. Electrons exist in atoms and molecules. And specifically, a handy place to put electrons, if you want to store them, is in covalent bonds. Because in a covalent bond, you've got a pair of electrons and they're being shared between two atoms, which keeps them in a quote unquote known location. They're hovering somewhere between the two atoms rather than just kind of careening around in the universe, which would be much harder to grab them because they're so small and they travel literally at the speed of light. So controlling electron location by putting the electrons in covalent bonds is a handy way to move them around without losing track of the slippery little guys because they're really tiny and they're really fast. So now let's go back to our TCA cycle, because the whole point of the TCA cycle is to make reduced electron carriers. The more FADH2 and NADH you make, the more electrons you can use to make that proton gradient. So that's the whole point of the citric acid cycle, is you need to move electrons in an ordered way, but they're too tiny and too fast to do on an electron by electron basis. So instead of moving individual electrons, you basically take electrons stored in covalent bonds. I'm actually going to do this. There we go. I want to draw on this. So, you know, in this particular drawing, which happens to have come from Khan Academy, the purple circles are carbons. And these are carbons that used to be part of a glucose, but we know that, that glucose has undergone glycolysis and become pyruvate, and that pyruvate has been transformed into acetyl-CoA. So these two carbons right here are the leftovers of what used to be a 6-carbon molecule called glucose. So we started dismantling glucose somewhere off screen, and now we're dealing with the carbons that are left over. So we have acetyl-CoA, and then an enzyme. So each of these little steps right here, there, all the little areas I just circled, all of those represent an enzyme. It's just that the enzyme name hasn't been written there to keep this drawing a little bit easier to look at. So these are all parts of enzymatic action. All right, so I've got an oxaloacetate from the last cycle, and now I have this new acetyl-CoA entering. So this step 1 here is just rip the CoA, coenzyme A, off of this incoming acetyl group and take the oxaloacetate that I had at the end of the last cycle, and I'm just going to glue them together. So if you count 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 5, 6. Oh, look, 2 plus 4 is 6. So that's where the citrate comes from. We're just taking a leftover and gluing it to a new thing. And in doing so, notice I've glued 4 carbons to 2 carbons. So I've formed a covalent bond. Right there is where I formed it, which means that I've now stored and controlled the location of 2 electrons, at least, because the definition of covalent bond is 2 atoms sharing a pair of electrons. So I take my citrate and my newly stabilized electron pair, where I'm like, haha, I know where you are, electrons. That means I can move you. And now I'm going to use another enzymatic step. And one of those bonds I just made, I'm going to break it. So now I have 1, 2, 3, 4, 5. So I broke this guy right here between carbon 5 and carbon 6. I broke that, which there was a pair of electrons shared in there. So NAD plus is the fact that it has a positive charge because it needs an electron. So if I put a E on that plus, I get H, because all hydrogen is, that's what the H stands for, hydrogen is a proton with 1 electron orbiting it. So if I have a proton hanging out by itself on the end of a bigger molecule called NAD, and then I stick an electron on that naked proton, I get an H at the end because 1 electron plus 1 proton is H. So that's how it goes from plus to H. The reason I'm being so explicit about that is because I remember being really confused by plus versus H for the entire time I was learning this in my undergrad, and no one ever bothered to explain it to me. So I'm going to try and do that for you. because I find that really confusing. Okay, so I ripped apart this covalent bond, which is a shared pair of electrons. And I put one of the electrons onto here, resulting in the H. And then the other electron actually ends up leaving inside of this CO2. The CO2 is one of the CO2s that you breathe out. So every time you exhale, some of the CO2 that you're breathing out actually came from these reactions. Okay, so hooray, I've made one electron carrier, and this is going to go off to the electron transport chain, and it's going to get used to try and push protons into that intermembrane space. And then I'm going to do essentially the exact same operation here. So I've got another NAD plus, and I'm going to pop another carbon off of this. So now we have 1, 2, 3, 4. Same deal. The electron that I'm stealing from this covalent bond, it goes on to the plus, giving us our H. And then this one goes off to the electron transport chain. And again, the other one ends up as part of CO2. And again, I breathe that out. So when we talk about CO2 as being a quote unquote waste product of metabolism, you might be wondering, like, well, where does that come from? It comes from here. All right, so now I have this little 4-carbon molecule, and we actually, in this case, have the phosphorylation, which is adding a phosphate too. So we have guanosine diphosphate, which is a nitrogenous base plus 2 phosphate groups, and I have an inorganic phosphate. So I'm going to glue these together. And you don't need to know the details of this reaction. That's not important at this level. Just that here you get a GTP, just one, but it has the same energy equivalent to ATP. So this step right here is not used to make reduced electron carriers. My computer is running out of batteries. This step is just used to make one quick and dirty, cheap little energy unit, which is used to power other things. And then we get the creation of a couple more reduced electron carriers. So again, manipulating covalent bonds to produce FADH2, which is an electron carrier, and then some other steps to produce another NADH. And these are just manipulating and rearranging the bonds here. The specific enzymatic steps between here and here are actually pretty complicated, but you don't need to know them for this class in that much detail. So you end up with oxaloacetate, which still has plenty of covalent bonds in it. And it just so happens that, oh, look, there's another acetyl-CoA coming in. So you glue those two together, and the cycle starts over. So really the point of the cycling of the citric acid cycle is to steal electrons from covalent bonds, put them in different covalent bonds, and then send the reduced electron carriers away and use them to make that proton gradient at the mitochondrion. So a good summary for all of this is just to say, the cycling of the citric acid cycle's purpose is to move electrons around so that they can be carried elsewhere and used to create potential energy. So I know that's a lot of information, and it's going to take a while to percolate, but hopefully now you understand a little bit better what the point of all this is, because at least as far as I'm concerned, there's no point in learning any of this if you don't understand why it happens and what relevance it has to you, specifically you staying alive, because you need this process in order to not die.
What makes more sense to me now is like I almost pieced it all together as a puzzle. So I saw how glycolysis like went straight to the acetyl-CoA, like they connected. I was like, where does the citric acid cycle connect to the oxidative phosphor, or you say it? And now I see it's really just as they're grabbing the electrons, they're just putting them out there right away.
Yeah, exactly. And like that piece that you were missing, you're like, well, how does the citric acid cycle relate to the oxidative phosphorylation? That was the part that I didn't understand for a long time either, until I was a little bit better at the chemistry. And I was like, oh, this is just a fancy way to move electrons around. That's all it is. So like the only reason oxaloacetate or citrate even matter is because they contain shared pairs of electrons that you can rearrange in ways that are more energetically favorable. And I'm going to end the recording now because I think that's all I have to say about that. No, that's not what I want to do. End recording. Sometimes I'm really bad at Zoom. Stop recording. There we go.